Alright, so today we will study three different methods of solving integrals. Basically the substitution rule, the integration by parts, and partial fractions. Let's start with the substitution rule. First, let's study the formula for indefinite integral. Okay, so here are the hypotheses. We set u equal g of x to be differentiable function with range and interval that I will denote I, such that f is continuous on I. Yeah, so here f and g are two functions, right? And we assume that g is differentiable and on a range where f is continuous. Then we have the following formula. If we want to calculate the indefinite integral f g of x times g prime of x dx, then this is just the indefinite integral of f of u du, where we have set u equal g of x. All right, let's give an example of this formula. Okay, imagine that you want to evaluate the indefinite integral 2x square root of 1 plus x squared dx. Then, in this case, you are going to set u equal 1 plus x squared, right? So u is a function depending on x. And then you will calculate du. So du will be, so here is like, yeah, or you can calculate this, right? U is a function in x, so you can, this makes sense, and this will be equal to 2x, right? Or from this, you deduce formally that du is equal to 2x times dx, right? So this is especially interesting here because 2x dx, you see, we precisely is equal to du. So by our substitution rule, we deduce that this indefinite integral is actually nothing else than square root of u du. And we know the integral of the square root. We know the antiderivative of square root. This is like u to the power half, and then we do 2/3 of u, and then we have to add this time the constant. Okay, so yeah, not a good point is to note that here we, even though it's indefinite, we don't need the constant because we have basically, more or less speaking, a constant on both terms. Okay, both terms are indefinite in this. But when you, at the end, when you want to evaluate indefinite integral, you will end up with a constant. Okay, so this is important point. Finally, you want to go back to the value, yeah, so sorry, so this was 3/2, right? Half plus 1. Yeah, so then you go back to what is u, okay? And you can write that this is just 1 plus x squared times to the power 3 over 2, okay? That's right. So, this works beautifully. And we have analog formula for the definite integral. Okay, so let's have a look at this. So after indefinite, let's find the formula for definite integral. Okay, in this case, we still have our two functions, and we are going to modify slightly the hypothesis here. Okay, so we will assume that G prime is continuous on some closed interval AB, right? And F is also continuous on the range of G. Remember, the range is a set of values G of x, where x belongs to this closed interval AB. Okay? So we will assume that J prime is continuous on the closed interval and that F is continuous on the range of G. If we have that, then we can conclude that the integral between A and B of F of Gx times G prime of x dx is equal to the integral between GA and GB f of u du. Okay, so let's have a look at this formula. On the left-hand side, basically you just add the bounds. G is a function from A to B, a closed interval, and you add the bound. Be careful, on the right side, usually students sometimes forget about this, you have to change the bound. If on the left it's A, on the right side it should be G of A and G of B. Okay, so this is a very important point. Now, let's give also an example. So, an example, so evaluate the integral between 1 and 2 of dx 3 minus 5x to the power 2. Okay, so here a smart move seems to be to set u equals 3 minus 5x. Okay, and then we do as before, we conclude that du will be minus 5 dx, isn't it? And we need also to evaluate, so here u is our g, it's like our g of x, and this is definitely a continuous function because it's a polynomial, and we need to evaluate, so the original integration on the left-hand side was between 1 and 2, so on the right-hand side it will be between g of A and g of B, which is u of 1 and u of 2. So we calculate also these values. And here they are minus 2 and minus 7. Okay. We conclude that the integral between 1 and 2 of dx over 3 minus 5 to the x and everything to the square, this will be equal to, so du, here we don't have the minus 5, isn't it? We don't have it here. So we need to do the usual trick. We are going to divide by minus 1 over 5, and then we can multiply by this minus 5 dx. Okay, so we will find our du, and everything will be fine. Okay, 3x to the square. Yeah. Using this little trick, I can rewrite, so here I'm still between 1 and 2, right? And here now I can use my letter, so this will be the integral, this time between u of 1, which is minus 2. Okay, so the integration will be between minus 2 and minus 7. This is just du, and this is just u squared. All right? Yes. So, yeah. So this is u minus 2. We know how to integrate this. We know the antiderivative. Basically, this is equal to minus 1 over 5, the antiderivative of minus 1 over u, and then everything between minus 2 and minus 7, right? And yeah, so I let you calculate this. You should find 1 over 14. Okay. So basically, you see how it goes. You try to think in advance what is going to be your change of variable, such that the thing is going to become integrable, right? So here, this choice is working perfectly because we end up by calculating the antiderivative of u to the power of minus 2, which is quite easy. And then, yeah, everything is going fine. All right. So this is for the substitution rule. Now the next rule I want to talk about is the integration by parts. All right. So let's have a look at this integration by parts. So these rules are used in for different integrals, of course. Sometimes, of course, one method will work for, two methods will work for the same integral, and then you have to find the best method, the method that is the less dangerous to use. Okay, so now how do we do the integration by parts? Well, I'm going to give you just the formula. So basically, the formula for indefinite, what is it? Indefinite integral. So this will apply when we want to calculate something like that. Okay, so obviously f and g are two functions, and g prime is g is differentiable. That's why we have some g prime. And we will need also that actually they are both differentiable. F is also differentiable. Then we have the following formula. The integral, indefinite integral of f of x times g prime of x will be equal to f times g of x minus the integral of g of x times f prime of x dx. Okay, so basically you have to use this formula. First you have to determine what is f and what is g, isn't it? And the g should be chosen such that this g prime, you know the antiderivative, okay? But sometimes you will know both antiderivative of the two terms, okay? So you will have, there is sometimes a choice in the integration by part formula, how to apply it, okay? Basically, if you know both antiderivatives, then you have a choice. So you try both, basically, and sometimes one is easier than the other. So, for example, yeah, let's see an example here. let's say that I want to calculate the antiderivative of x sine x dx. Yeah, so this is definitely a case where I know both antiderivatives. So I can really consider, so here I'm going to consider f of x as x, and g prime of x, I will think it as sine of x. But here I could really use both. Then if I do that, well, I know the antiderivative of sine x, isn't it? So this will be cos of x, isn't it? And then, minus cos of x, yeah, because when you derive g, you get another minus. So minus cos of x, and then you can use your formula here. So the antiderivative of x times sine x will be dx, sorry. No, I didn't forget the dx. So it will be x times the antiderivative, so times minus cos x, and then minus the antiderivative of g, so minus cos x times f prime. So f prime is just 1. Yeah. So this is quite good. So what do we get? We get minus x cos x, and here we get minus minus plus the antiderivative of cos x dx. Okay. And so what do we get finally? We get minus x cos x plus sine x, which is an antiderivative of cos, and here we need to finish by the constant. Okay. Now, interesting exercise, for example, would be exercise. You can try to set f of x equal sine of x, and g of x, g prime of x equal x, right? You can try. You can apply both formulas, but you will see that with this one, you will not really conclude anything, okay? So sometimes integration by parts will complicate further the integral. Sometimes it will solve it, and you can apply in both situations, okay? So just find the right, here you really need practice to have the intuition which one is going to give you the solution, and which one complicate your life. Okay, now what about the definite integral case? Definite integral. Okay, so basically we need, of course, the same hypothesis here. Let me find the formula. Yeah. So basically the formula here will be as follows. If you want to integrate between a and b, an integral of the form f of x times g prime of x, right? Then this will be, so here you are going to use this symbol. Okay, remember this means that you evaluate first at b minus this evaluated at a, okay? And then, not surprisingly, the definite integral of g of x times f prime of x dx. Okay. Do I want to give an example about this one? Let me see. Yeah, we will see many exercises. So, yeah, I don't give any example. Of course, you can take the previous example, and yeah. So let's see. Let's do this as an exercise. You can evaluate the integral between 0 and pi of x sine x dx, right? Okay, you can do that. We will do many exercises. So in the exercise section, so don't worry about it. So basically, this is the two fundamental rules of integration: substitution and integration by parts. There is another case we want to study, and which is called partial fraction. Partial fraction, so this is a method to evaluate integrals of the type okay, so here you will have p of x divided by q of x dx, where p of x and q of x are polynomials, and of course q of x is not 0, right? Okay, basically rational functions. Okay, so how can we integrate rational function? Well, let me start by an example. Imagine that you want to integrate x plus 5 divided by x squared plus x minus 2 dx. Okay? Now, the trick, first of all, we are going to rewrite the denominator. So, what we can say about the denominator is that this x squared plus x minus 2, this can be written as x minus 1 times x plus 2, right? You use the usual discriminant formula, or you can find easily this factorization. And then we can write x plus 5 divided by x plus minus 1 times x plus 2. Yeah, we can write it as 2 over x minus 1 minus 1 over x plus 2. So this is wonderful, because here this is a priori very difficult to calculate the antiderivative of that. But the antiderivative of this on the right side is obvious, isn't it? Is basically will be calculated using the logarithm function, right? So once you have observed this, you can conclude that the antiderivative, I mean the indefinite integral of this will be actually 2 times the antiderivative of x minus 1 dx, right? Minus the antiderivative of x plus 2 dx. And this is extremely easy to calculate, because, as you know, this is just 2 times the logarithm of absolute value of x minus 1. Be careful, most people always forget the absolute value. Don't forget the absolute value. And minus logarithm of absolute value of x plus 2. And you evaluate some indefinite integral, so you need a constant, right? There will be always a constant. Okay, so what do we have to remember about this example is that there is no substitution really, or integration by parts that would be useful here in this case. You need to find another trick. The trick is to write the denominator as the product of 2 terms, and then by the rules of fraction, you know that you can decompose this kind of fraction like this, okay? So this was a term of degree, or this was a polynomial. The denominator was a polynomial of degree 2, and you transformed it into a polynomial of degree 1. And you know the antiderivative of each, so it becomes easy. So in general, when we are given a rational function, which is a fraction of two polynomials, how do we proceed? Okay, so we want to follow this exercise, but what can we do when we have a general rational function? Okay, that's the game. So, what is the data? So let's see a method to evaluate the integral of p of x divided by q of x dx, where p of x and q of x are polynomials. So we will have several steps to do such work. First of all, step 1, we will have a look at the degree of the polynomial p and q. So if the degree of p is greater or equal to the degree of q, then we can divide p of x by q of x. So basically we will use the so-called Euclidean algorithm and get p of x equal q of x times something, s of x, plus another function r of x, such that the degree of r of x will be strictly less than the degree of q, and will be, yeah, that's all. Well, obviously, positive or equal to 0. That's right. Yeah, no, sorry, it can be something else, actually. So we will have this, yeah, we will have this. And then, yeah, let's give an example of that. So I don't know if you are used to calculate Euclidean division of polynomials, but it is quite easy. So let's take the example of x squared plus x divided by x minus 1. So this, how do you do? Well, you write it as a fraction, so everybody has his own method to calculate fraction. Me, I know this one. So how many times x squared plus x? So if you get x times this, you will get what? You will get x squared minus x, isn't it? And now you remove it, and the remaining factor is 2x, okay? So here you get plus 2. Then you will get 2x minus 2, isn't it? And you divide this, you subtract this, so you will get 2. Okay, and then you can write, once you have done this, that x squared plus x is equal to x minus 1 x plus 2 plus 2. That's right. So in particular, I conclude what? I conclude that x squared plus x, and here I divide by x minus 1, right? This will be equal to x plus 2 plus 2 to x minus 1, right? And I can integrate, calculate the antiderivative of x plus 2, and I can calculate the antiderivative of this. So now I can evaluate basically my integral. Okay, so once you have done this, this is super. So if we want to, yeah, I let you conclude, but exercise, evaluate the integral, indefinite integral of x squared plus x divided by x minus 1. Yeah, this will, using the partial fraction method, will give you the answer. Okay. So sometimes, yeah, let me write this down. Sometimes it is not enough to conclude. So why is that? Why it is not enough to conclude? Since so you can have the case where r of x divided by q of x, this can be complicated. This can be complicated. In such case, so here, you see, we have divided by q, okay? This was our q of x, and we divided by q, and we get the rest, the remainder divided by q was something integrable, okay? So here it was easy, but sometimes this remainder divided by q of x will be not immediately integrable, and so we will, so in such case, we have, so we need a second step, okay, second step. So what is a second step? It will be, which consists in factorizing q of x. So you see, again, you divide by something, here it was of degree 1, and so it was very, very easy to integrate. But if it's of degree bigger, then you factorize it in different terms, and then you write it like this, similarly. Okay, so in fact, so this is a fact that I won't prove, but any polynomial can be factorized as a product. So basically here I'm talking about the case in R of x, right? In the ring of polynomials with real coefficient. Because maybe you know that we have the so-called fundamental theorem of algebra. You have seen that in linear algebra, that says that any polynomial can actually be factorized in, so if a polynomial is of degree n, you can factorize it in terms of n factors, right? But the roots can be complex, okay? So here, if we want to remain in real numbers, then we can factorize as follows. So basically, it will be a product of linear factors. So by this, I just mean polynomial of degree 1, okay? And irreducible factors of degree 2. Okay, so it's a non-trivial fact, right? You can always, so degree 2, which means ax squared plus bx plus c. But something that irreducible means that you cannot split this one into two terms. It means that if you were doing this, then the root will be I, complex number, and its conjugate. Okay? So if you want to stay in the realm of real numbers, then you cannot do that. But anyway, even any, for example, degree 3 polynomial, you will be able to factorize it in the following way. Okay, so now an example of this fact. If I give you x4 minus 16, then you can apply a square minus b square equal a minus b, a plus b. So you will see it's equal to x square minus 4 times x square plus 4. So this one is irreducible, you cannot factorize it further. And this one is not irreducible, and I can write it as x minus 2, x plus 2. Okay, so you know, you have a polynomial of degree 4 and you transform it into a product of linear factors, okay, 2 linear factors and 1 irreducible polynomial of degree 2. Okay, so you do that for q of x. Okay, you do your factorization like this in linear factors and polynomial of degree 2. Then what can you do with that? So this will be step 3. Step 3, right? So basically, we express our remainder divided by q of x, okay, as a sum of a. So the linear factors, you will be able to write them like this, right? Ax plus b. You will have terms like this. So if they repeat, of course you can have several times the same linear factor, in which case you will have something like that, to some power, okay, power I. Or you will have something of the form ax plus b divided by ax, okay, so it's not the same a, so I don't know, b, no, let's write a2 x square plus a1x plus a0, okay, and again this term could come several times, so you would put it to some power j. All right. So by the so-called fact, it is always possible to do so. All right? Now, once you have done this, case 1, you have several, many cases actually to consider. So your q of x can be decomposed into linear factors. Imagine. So you will have typically something that you can write a1x plus b1, and then you would go until some k, a kx plus bk. So k terms of degree 1. Then, so here, when I write this, no factor is repeated. So I don't have this power here. No factor is repeated, and no factor is a multiple of the other. Okay, multiple, which means 2 times this one, for example. Because if I had this time 2 times this one, then I could write the 2 here, and this I will get a square. So I don't want squares, okay? So this is case 1. I really decompose in n, in k linear term distinct, okay? And in this case, okay? So in this case, what can we do? Right. Then we can write, this is the easiest case, in fact, because in this case we can write r of x divided by q of x as really capital S over a1x plus b1 plus, okay, let's call it capital A1, and then plus akx plus bk. Okay, and here now we can integrate easily, so then we can evaluate easily, right? Now let me give you an example of this. Okay, imagine that you want to evaluate x squared plus 2x minus 1 divided by x times 2x minus 1 x plus 2. Okay, so first of all, you observe that the denominator has higher degree than the nominator, so it's already of the form r of x divided by q of x. So you don't need to apply step 1. You just go to basically step 2 is done also. You can write easily q of x, you can decompose q of x, and then for sure you know that we will be able to write this in the form x squared plus 2x minus 1 divided by x minus 1 times x plus 2. So we can write this for sure as a over x plus b over x minus 1 plus c over x plus 2, right? And so again, the problem is to find a, b, and c. Because once you have found a, b, and c, then you will be able to integrate easily. So how do we find a, b, and c? So this is quite easy. We, let's get call this star. So we are going to multiply both sides by the denominator, 2x, so 2x, so this was 2x minus 1, right? 2x, yeah. 2x minus 1 and times x plus 2. So if I do that, what do I get? I will get x squared plus 2x minus 1 equal, so here I will get a times the two remaining factor 2x minus 1 x plus 2, and then plus b, and here what will remain is, okay, so here again it was 2x minus 1. So what will remain is x plus 2 times x, right? And finally c times x and 2x minus 1 and x. Yeah. Okay, we do that. Now, how do you do to find a, b, and c? Well, put x equals 0, okay? So the first, what happens? So basically you are going to evaluate this at all the roots. So you have the roots x equals 0, x equal half, and x equal minus 2, right? So if you put x equals 0 on the left, so you will find, basically, so you evaluate this at 0, so you find minus 1. So let's put this 2 star, right? So put this in 2 star. What do you get? You get on the left, evaluated at 0, minus 1. And then here, what is happening? Well, everywhere where x was a root, so here and here, this is equalized to 0. And then here, you will get a times, so minus 1 times 2, right? And as you can see, you can find easily your a, so a is equal to half, right? So this is cool. Now you do the same, so you put x equal half, you will get b, the value of b, and you will find 1 over 5. And then you put x equal the third root minus 2, and I let you do the calculation. You should find c equal 1 over 10. Now, if you put again in star this value for a, b, and c, you see that now you can evaluate. So, exercise, finish the evaluation of integral of x squared plus 2x minus 1 divided by x over 2x minus 1 divided by x plus 2. Okay. So, as you have seen, this was case 1, the case where the denominator q of x can be written as a product of linear terms distinct, okay, no degree 2, and you can degree 1, degree 1, degree 1, then you can write it like this way. You multiply by the denominator, you get this formula, and then you determine a, b, and c, or you can have more. This will work very easily. Okay, now we have to study another case. Let's go here. Case 2. Case 2, q of x has some repeated factor of the form of a linear factor. So something like a1x plus b1, but not to the power 1, but to some power, so power r. Okay? Now, what do you do with this kind of case? Well, for sure, you can write r of x divided by this guy, a1x plus b1 to the power r. You will be able to write it as follows. Basically, it will be equal to a1 over a1x plus b1 plus a2 a1x plus b1 to the power 2 and 3 dots plus a r a1x plus b1 to the r. Okay, so basically, if you have this kind of term to evaluate, then you can write it. So r of x, remember, can be a polynomial of any degree, right? But you will be able to replace that by some just constant, okay? And after that, a substitution rule will give you easily the integral, okay? You just set u equal a1x plus b1 and you will get something to integrate of the form 1 over u to some power, and you know how to do that. Okay, so you can conclude when you have this. Now again, how to find the a1, a2, ar. So to find the ai's, let's say, use the previous method. So you remember is very easy. Okay. Now, yeah, actually, this does not give the solution for all rational functions. Okay. There are some cases that can be nasty. For example, you can have degree 2 factors repeated, okay? And then you need, so there are more cases to be considered. But we won't do it. If you encounter an integral with, so basically this could happen if your q of x has some repeated factors of degree 2, okay? This is a quite difficult case. In such case, you apply similar methods, but to cover all possible cases is too long, so I basically will stop under these two cases of interest. Okay, thank you. I think I will stop here, and next time we will study improper, so-called improper integrals. Thank you very much.